So, this homework, I think, is very interesting. So you've got spring break, which you should enjoy, but kind of put this in the back of your brain pan, play around a little bit. So A, B, C, and D are real numbers. A is less than B and C is less than D. Show that there's a one-to-one onto function from the interval AB to the interval CB. So, in fact, you can probably make it in here. This is not too difficult to do. Maybe send A to C and B to D and just linearly do this. But whatever function you use, you should show that it is one-to-one onto. So in other words, what we're saying is the interval from 0 to 2 and the interval from 17 to 300 have the same number of elements in it. Those two sets are the same size because there's a one-to-one and onto. C, I think, is the harder one in there. You'll have to think about this one. Show that there is a one-to-one and onto function from the open interval from AB to the interval C closed D. So in a certain sense, this one's got an extra point. An easy way to do this is you might start off by showing that there's a one-to-one and onto function from the interval 0, 1 to 0, 1, and then use compositions of maps to get this more general case. Number C, show there's a one-to-one and onto function from AB to R. The most obvious one to me might take you back to calculus or even trigonometry days. Number 2, we had an earlier problem where we considered the set of functions from R to R. We also considered an equivalence relation on this set by declaring two functions are equivalent if their difference is continuous, and another equivalence relation by declaring that two functions are equivalent if they're differentiable. EC was the equivalence classes under the first relation, and ED the equivalence classes under the second. Show there's an onto function from the equivalence classes of D to the equivalence classes under C, and show there's a one-to-one function from the reals to the equivalence classes under C. That one shouldn't be. I don't think that one too. This one will probably require some thought. Let A, B, C, D be real numbers. Again, A is less than B and C is less than D. And capital A, B, C, D be sets. For this problem, you may assume without proof that the decimal expansion base 10 of a real number that does not end in a string of zeros or nines, that if the decimal expansion of a real number does not end in a string of zeros or nines, and the decimal expansion is unique. For extra credit, prove this, but don't turn it into the homework. If you're going to do the extra credit, just email it. So for example, y'all are familiar with like 0.50000, 0.5 is equal to 0.4999999, right? But anything that doesn't end in an infinite string of zeros and nines is unique. That might be useful in person. Show that there is a one-to-one function from A cross B, AB cross CD to the interval 0, 1. My hint here is first find a one-to-one and onto function from 0, 1, 0, 1 to 0. By the way, it's easy to get an onto function there. It's easy to get one-to-one. How do you get 0, 1, 0, 1 to 0, 1? How are you going to do that? My hint is think zipper, think merging traffic. Might help. Show that there is a one-to-one, and finally show that there's a one-to-one function from R cross R to R. So in other words, how many points are there in the plane? The same number of points that there are on the line, right? There's no difference there, right? Because this set, which is the plane that you used to in calculus, and this set, which is a line, essentially, they have the same number of points on it. That's what this problem shows. And finally, in number 4, in this problem, we will construct a function from the natural numbers to the rational numbers that is onto, that covers everything. First, find a function from n to n cross n that is both one-to-one and onto. Explain in part B how this can be used to contain an onto function from the natural numbers to the positive rationals. And finally, bootstrap this and find a function from the natural numbers into Q that it's on. Okay, so this one, some of these problems will actually require a little thought about how to do this. So think about that. And let me know if you have questions. Okay. So let's pick up where we left off. Any questions when we get rolling? Okay, so left off here. So I'm going to give you a couple of, the last theorem I gave you was this business about how to add up elements in finite set. We've talked about this before. I give you a proof in the notes. So I'm going to move on to I'm not going to prove this because this actually follows from the previous result. Let n be a natural number. And actually, I want the natural number to be bigger than 1. If x is an nm, and remember this is the numbers 1, 2, 3 all the way up to m. Then so in other words, what this says is if you have n sub m, these are the numbers 1 through m, and you take one of them away, then that set of elements is in one-to-one correspondence with n minus 1. This is not shocking, and actually follows from the previous result. But we're going to use this in the following. This is a sort of one of those theorems. It's actually kind of obvious, and you think, well, okay, that's an obvious statement, so it can't be useful, but actually is. This is how many of you have ever heard that buzzword, the pigeonhole principle? This is the famous pigeonhole principle. Basically, some people talk about it as like a mail slot, right? So if you've got like a bunch of mailboxes and there's 101, there's 100 mailboxes, and the post person delivers 101 letters, somebody's getting more than one letter, right? Because there's 100 boxes to put it in, so at least one person has to get one letter. This is an equivalent way of stating this. I'll do it the fancy pants way. But n, be natural numbers with n the bigger one. So n is properly bigger, or is strictly bigger than m. If f goes from n sub n to n sub m, then f is not 1. So what this says is this is a bigger set than this. They're both finite. This is bigger than this. You can't make a one-to-one function from a bigger set, a properly bigger finite set, to a smaller set. Let's prove this. We'll go by induction on n. So my base case here should be n is bigger than m. Our base case is n, right? Because I have to have m to be strictly smaller. So there's only one natural number that's less than two, strictly less than two, and that's one. And notice the only function the domain of this, they've all got to go somewhere. There's only one place to go. This certainly is not one to one. And this is in fact the only function. That's it. The only function from the set of two elements to set of one element is that. And it's not one to one. Everybody okay with that? So there's the base case. Now assume that for all k less than or equal to n, there's no one-to-one function from n k to n. And there is no one-to-one function from n k to n. Okay, so this is our inductive hypothesis. Now let's consider the case where we have n plus one elements. Now, suppose. Now, let's consider n plus one. N plus one. And suppose we have a one-to-one function. Yeah. Where n plus one bigger than. Suppose that we actually have some function from n sub n plus one to n. And what we're doing, of course, is we need a contradiction. Well, let's consider the restriction of this function. So to get contradiction, consider the restriction of f to n sub n. So we're going to just consider the function with the domain now, not the first n plus one numbers. Natural numbers, but the first n. So the range of h cannot contain f equals one, right? Because the fact the function, we're assuming that this is a one-to-one function. So n plus one went somewhere over here, and the range of the restricted function cannot contain this. Because if there's something in the restricted function that goes here, then that means the original function f is not one-to-one, right? So what this means is now we have h is a function that goes from n sub n to n sub m minus set D, where D is in one-to-one correspondence with n sub m minus single point. But by the previous lemma, we know that n sub m one correspondence with n sub m minus one. That's the previous lemma. This thing, take away this, you've got one less element. So this gives a one-to-one function from n sub n into n minus one, and this is a contradiction. Because our inductive hypothesis says there can be no such function. This gives the pigeonhole principle, which basically says no one-to-one functions from finite sets if the domain is larger than the codomain, right? It means that if you have 10 mail slots and 12 letters, then somebody's going to get more than one letter. Obvious when you think about it, but this is actually quite useful. Here's the first corollary, which you may scoff at as well, but I'm going to use this corollary and we'll have last corollary. I don't think anybody will be surprised at this. What you may be surprised at is the application. A finite set is not equivalent to any of its problem subsets. Finite set. Then X is not equivalent. Uh, Let me write this another way, hopefully to induce clarity. If y is contained in X and is proper, then the statement says right? You can't go buy a dozen eggs and throw one of them in the garbage and still have a dozen eggs, right? You can't do it, right? No surprises there. Let me actually prove this thing. X is finite. Cardinality of X is cardinality of n sub n. So, you know. By the way, let me point out, if X is the empty set, then the empty set has no proper subsets in the first place. So there's nothing we'll consider with the empty set. So we'll assume that X is finite, not empty. Then the cardinality of X, then X is equivalent to n to the n. So I'm going to do this proof for that. And then general case follows very quickly. Because the only proper subset of N1 is the empty set. right? And certainly this holds, right? So a set with one element is not equivalent, not the same size as the empty set. Now assume for some K1, the hypothesis for some K1, figure that out. So, sorry. Now assume for some K bigger than 1. NK has a subset S. And also a one-to-one and onto function. In K, in sub K, the S. So let's break this down in cases. The first case I want to consider is if K is not an S. Not an S. Then we can construe S as a subset of NK plus 1. If S is a subset of NK, and if K is not an S, then it's not K plus 1. K minus. If NK is not in there, then it's a proper subset of NK minus 1. And hence there is a one function. There exists a one-to-one function from NK into NK minus 1. Because actually this one-to-one function into S would be a subset of NK minus 1, and this is a contradiction. Because there can be a one-to-one function up to a smaller. In the second case, suppose that K is in S. On the other hand, K is in S. Well, we know that S is a proper subset of N sub K, so there is something as S is a proper subset of N K. There exists an M K minus 1 such that M is not in S. Now, used bijection from n k minus one to itself. In k to itself, that exchanges m and k. So this function here takes every number to itself, except it takes k to m and n to k. So it just reverses m and k. And now apply. So it seems like a long proof to go through, but on the other hand, there you have it. And this is a rather important result. If you have X being a finite set, then X is not equivalent to any subset. Any proper subset must be smaller. Questions? How many do you think this is silly? It's a little silly, seems like. Looking at application, which might be a little bit surprising that this is useful. So now I'm going to do some minimum. Now we start doing some fun stuff, even more fun stuff, I should say. Theory. Let's hit the ground running. How many of you agree with the statement? Set of natural numbers is infinite. Prove it.
Or any in the natural numbers, n plus one is also a natural number.
Right, that's true. I mean, that's actually one of the basic things that we use to derive it, right? So how does that help?
Because then it means you have any set of finite set of natural numbers, the next one is also in that sense. You always add one. Never add finite.
Right, you could do that. Use some of the previous stuff we did, use some kind of argument like that. Let me give you a cool argument for this. It's the even match. Right? Everybody agree this proper subset of natural numbers, because I mean, after all, there's no odds there. Consider f and n to n given by f of n. Everybody agree this is on to? So one is right. Here's what I. That makes the function n equals to m, which implies n equals to m. So by our earlier definition of equivalent, these two sets are equivalent. They're the same cardinality, right? So it's a one-to-one and object function. But 2n strictly contained in n. So by 5, 1, 13, n cannot be defined. Because here, this corollary has no set, no finite set is equivalent to a proper subset. But here, this set is equivalent to a proper subset. It can't be finite. So that's a really kind of groovy application. Yes,
Wait, so how is the order of maximum and the order of the denumerability?
this is a definition. This is what it means. I use this notation, part of the bar. So let me remind you of what that's all about. X. There exists a bijection. This is what we meant for two things to be related. They have same, and I also use the notation. Means that there's a one-to-one or two. And that's how we were going to define the cardinality the same. In fact, I'm going to give you a definition here that'll show you, that'll tie everything together.
How is like the natural not greater than, like, how are there not more elements than just the natural?
Well, see, that's the problem, isn't it? I mean, how do you count the infinite, right?
Oh, there's.
Right? I mean, and this is exactly the way we define it. Our intuition is this is silly if you have a finite set, which is true. I know that there's more people on the first floor of the class than on the second day, and way more on the third. That's the empty set. But this is how we count infinite sets. And this was actually a problem that mathematicians struggled with for a while. How do you count the infinite, right? Is the integers bigger than the natural numbers? Well, it would seem to be, right? Because there's a one-to-one map from the natural numbers into the integers. And the notation confuses you, right? Because it's like, oh, look, it's half of the integers. Right? This should be half of the natural numbers, right? But on the other hand, these are in one-to-one correspondence. And that's how you have to handle them, right? Is to say, pair them off, do a bijection. In fact, here's a definition that will address this. Definition, notation as well, probably. Set, let A and B sets. You say. There is this bijection. Yeah. From A to B. Or equivalently one from B to A, so this is an equivalence relation. We say that cardinality of A is less than or equal to cardinality of B if there's a one-to-one function. So if there's a one-to-one function from here to here that may not be onto, we say that this is A cardinality of A is less than or equal. Equivalently, there exists onto function. B to A. So you can think of that either way. We say A is strictly less than B if there exists a one-to-one function. H may be, but no onto function. So we say that the cardinality is strictly less if there's a one-to-one function from here to here. But no onto, or in particular, there's no bijection, right? And you can one-to-one, but no onto. Equivalently, you can say another way, as you might expect, is there's an onto function here, but no one-to-one function in that direction. So here are some things that we have. Here's another definition. We say that a set S is denumerable if we say that a set is denumerable if it can be put in one-to-one correspondence with the natural numbers. In this case, we say that S has cardinality and here's a shout out to my 5-year-old. I like the knot. I did a terrible job. This is the first letter of the Hebrew alphabet. It's called Aleph, and sub-zero. This symbolizes the size of infinity. It corresponds to the natural numbers. Example. These sets are all denumerable. I've shown you some of these, and some of these we will get to. Theorem. Here's kind of an interesting sort of theorem about this. I'm gonna hopefully be able to prove 2 of them today. Let A and B be denumerable, then so is the set A plus B. So if you have a denumerable set, if you A and B, if you have ordered pairs of this, it's the same size. First show. And probably this is all I'm going to show, but I'll explain to you how to patch it together. I'll first show that n cross n is n. I'm going to define from and I'm going to define it this way. My input are 2 natural numbers, n and m. My output okay. First of all, would everybody agree that when I put in 2 natural numbers here, n and m, my output here, this is a natural. right? It's power of two times some odd number, and since m is at least one, this is at least one, so. Let's do 1-to-1 first. Here in a there numbers. This means two to n minus one. What do I know about these two numbers? What odd thing do I know about these two numbers? These in front of me. They're odd, right? Now, remember, the fundamental theorem of arithmetic tells me that prime factorizations are unique, right? And so the number of powers of two on these two sides must be equal. Right? And I know there's no extra twos hanging around in here or in here because these are odd, right? This means this should be a nice on that. Now that I know the powers of two are equal, I can subtract, or I'm sorry, divide, and I get 2m minus 1 equals 2b minus 1. 2m equals 2b. M equals b. So n equals a, and n equals b. So the order pair n and m is equal to the order pair a b, and f is 1 to 1. Everybody okay with it? Why is it on to? This is kind of fun because if n equals 1, then f of 1, 1 is equal to 1. Right? I agree. And if n is bigger than 1, then the fundamental theorem of arithmetic. So I can write n right. I can write n as 2 to the a times p1 a1 up to pk ak, where ai are in the natural numbers and pi's are all electrons. Do I agree with that? And actually, I'm going to streamline this. This thing is odd. So this is in the form 2b minus 1. Because any odd number can be written in this form. Everybody agree? And this is f of, I guess, a plus 1. B. Because subtract 1, and that's your exponent of 2, and then 2. So it's 1 to 1 and on to. To do the more general case, just do what we did last time when I showed you that when we talked about if there's a 1 to 1 and on to function from a to n and b to n, then show that when you compose that with those functions, you get what you need. Okay. These are all infinite sets. Everybody agree with me? Let me give you something that you might find surprising. Theorem. Thanks. This is the natural numbers, and this is the set of numbers on the real line that are between 0 and 1. Every point on the real line. But everybody agrees these are both infinite sets. This one genuinely big. Does that surprise you? There's actually bigger infinities to start. Let me prove it. Note that this function. This takes 1 to a half, 2 to a third, 3 to the fourth, and so forth and so on. This is a 1-to-1 function. Everybody agree with that? And it misses a lot of points in here, right? It misses 0.9, it misses pi over 7, things like this. But 1 goes to a half, 2 goes to a third, 3 goes to a fourth. This is a 1-to-1 map. So we know that, oops, less than or equal to. What we really need to establish is you can't cover this. It can't be done. It doesn't cover it with this map. So I want to go over this again after break, but suppose there exists a bijection. From natural numbers to 0 to 1. And I'm going to write this out in decimal form. 1, 2, 3, and 1, 2. So I'm going to write this out in the base 10 decimal expansions. And if anything ends in a string of 9s, I'm going to replace it with a string of 0s. The next decimal place. So suppose we have a bijection, right? That means that every real number in the interval from 0 to 1 is somewhere in this right column, right? Let me construct it. I'm going to bring a following number. And here's what I'm going to do. I'm going to let BI be 2 if AII is not 2. And 3 if AII equals 2. So everybody agree, what is BI going to look like? It's going to be a string of 2s and 3s, right? And it's going to depend on what AI is, right? So for example, if the first decimal here is a 1 or a 6, then the first decimal of this will be 2. right? On the other hand, first, if this is a 2, then this would be 3, right? Notice that there's no ambiguity here because this decimal is a string of 3s and 2s, so it doesn't end in an infinite string of 9s or an infinite string of 0s. So this is unique, right? B1, B2, Bn forever must be in right column somewhere. Right? Because this map's supposed to be on to. So this new thing that I've created, this is certainly a decimal. It's a string of 2s and 3s. It's between 0 and 1. It's got to be here somewhere. Agreed? Has to. Well, where is it? Let us find it, shall we? Could it be this one? No, because it disagrees in the first decimal place and it doesn't end in a string of 9s and 0s. Can it be this one? No, because it agrees in the second, it disagrees in the second place. Can't be that one. Can it be this one? No, because it disagrees, by the way I built it, with this decimal. And doesn't end in a string of 9s and 0s. Can it be this one? No. This decimal, which is an honest to goodness decimal between 0 and 1, cannot possibly appear in the image of the map. So there is no bijection from n to 0, 1. So the natural numbers is strictly smaller. Now this is a whole can of worms we've opened here. Because now we've got an infinite set that's actually. Okay, I'm sorry, I went 2 minutes over, but it's just too much to ask to quell that type of excitement. Any questions?
Okay, so how can like A22 not, like I thought you wanted to, like you want eyes to be.
Well, see, here, so A22 and B2 don't agree. Second decimal place doesn't agree because I defined B2 to, how I define B2 will always be different than the decimal that appears in A22.
Oh, okay.
Right, so I've done this, I've sort of set this up for failure in a certain sense, right? Okay, we'll talk about this again some on Monday. I hope to see you all in the Labs Club, and I hope you have a great spring break.